we're going to get this show on the road. All right. So welcome to the Global Math Department, everyone. My name is Lee Natero, and I'll be your host tonight. Tonight, we're going to be hearing from Michael Pershan about why kids learn from examples and why other times they don't. I know a lot of you already introduced yourselves into the chat, but if you haven't done that, please do so, letting us know what you teach, where you teach, and what your Twitter handle is, if you have one. So glad to see so many people here tonight that are familiar names, and hopefully at some point in the future at a face-to-face conference, you'll be familiar faces. So before I introduce our speaker, let me explain how these meetings work. These meetings are recorded and are available within 24 hours after the meeting ends. To view the recording, you can use the same URL you used to get here tonight. The Global Math Department community prides itself on being friendly and supportive. The chat room is available for topical and general conversation throughout the meeting. I'll catch your questions for the presenter, so don't worry that the presenter won't notice your question in the chatter. Tonight, our speaker is Michael Pershan. Michael teaches math to 3rd, 8th, 9th, and 12th graders at St. Anne's School in Brooklyn. He's the author of a new book, Teaching Math with Examples. Michael has been blogging about math and teaching since 2010, including at mathmistakes.org, where he still occasionally publishes new mistakes. He is the former chair of the Global Math Department and way back when helped with the creation of the Global Math Department newsletter. So welcome, Michael.
Thank you so much. It's so nice being here. I should have started, right? We're ready to go?
Go ahead. Yeah, we're ready to go. Yep.
Okay, let's do it. So it's super nice to be back here. And the talk is why kids learn from examples and other times they don't. And it's inspired by parts of my new book, Teaching Math with Examples, which is for sale by the publisher John Catt Educational, and also on Amazon. And what I'm excited to talk about is some of the ideas from the book, especially in relation to like my teaching in this past year, and just a little bit about my teaching. It's not like I specifically always teach just 3rd graders, 8th graders, 9th graders, and 12th graders, and like one 11th grader this year. I'm at a private school where the math department covers the same like group of like, I don't know, 15 teachers, covers all the math teaching from 3rd grade all the way up to the end of secondary school, the end of high school. So what we teach changes depending on the year, but I often usually teach like some combination of elementary, like fractions and adding and multiplication, all that, and shapes and definitions and all that good stuff. And for the first time ever, I'm teaching calculus this year to a group of students who, it's not an AP calculus class. It's kind of a calculus class for people who don't want to take a college level calculus class. So that's my teaching life. To start, I want to share one of my favorite resources right now to share with kids is this website, Complexity Explorables, which I'm sure somebody can find and put into the chat. And for me, I think it explains, I'll explain a little bit about what this is, and then I want to just kind of use that as to comment on how I think about teaching and education. This website is beautiful, by the way. It's all about complexity studies, examples of something that my bare bones understanding of this is that once computers became cheaper and accessible to scientific researchers, it changed how people were able to formulate scientific theories. It used to be that if you wanted to have a theory of something really complex in nature, or something really complicated that an animal does, or that appears in some other natural setting, you needed a really complicated theory, because in order to generate complicated behavior in your mathematics, you need some really complicated mathematics. What computers changed is that you could instead have very simple rules and ask a computer to iterate them over and over and over again. Those simple rules, have them repeat over and over and over again, and get complicated behavior that way. So complex behavior can come from really simple ideas played out over and over and over again. And that's sort of central to how I think about teaching, even though it's kind of like a weird analogy. There's a lot of ways. I think sometimes what I don't love, or what I have a hard time with in education and teaching, is when we either ask like really complicated questions or give like super complicated answers, and they become hard to manage. So what I like to do is I like to say, let's try to ask simple questions. Let's try to give simple answers, maybe 2 simple answers at first, and then play them out. And so that's what I wanted to talk about. Like, I want to ask the question, why do kids learn from examples? Sometimes, if we give examples to students on the board or on a slide or whatever, or they can read them in a textbook, or we explain something, sometimes kids learn from those, and other times they don't. I wanted to ask the question, why? Why do kids sometimes learn from examples, and other times they don't? I should start, by the way, by just making sure we're on the same page of just kind of what I mean by an example. This is an example of an example. I took it from Math by Example, which is another fantastic resource. It's a group of researchers that partner with school districts to create materials that are example based. So this is a worked example, and this is like for, I think, either a 4th or a 5th grade class. And what it is, fundamentally, a worked example is a problem with a solution, and you're telling students you're going to learn from studying this solution. So it's not the learning is not supposed to happen primarily from solving the problem. It's primarily going to come from studying the solution. And by learning, what we mean is something like be able to solve a problem like this, or be able to solve some other problem after studying this example. So this is what I mean by a worked example. And so the question is, how does learning from worked examples work? It sometimes does, sometimes does not. Sometimes, and there's lots of maybe kind of easy answers that we could come up with that for why it doesn't work. Like, oh, it's not the right level. Kids don't get it. But when it does work, how does it work? Not magic, right? It's not, you show a thing, kids look at it, they don't magically be able to solve new problems all the time. There's something deeper happening here. What is that thing? So what I propose doing is shifting the question a little bit and saying, okay, so how does learning from problem solving work? Let's treat these as kind of similar questions. Let's first talk about how learning from problem solving can work, and then use that to talk about how learning from worked examples might work. I think that's a good perspective on this. So same question, how does learning from problem solving work? If you ask students to solve a problem, maybe they're successful, maybe they're not. How would they ever learn how to solve similar problems in the future? How? Okay, so one answer comes from a bunch of different sources, including Polya, the kind of problem-solving mathematician guru of problem solving. And if you've ever read his, I mean, I don't know. I feel like my first exposure to Polya was like seeing on a wall somebody have a poster that's like, oh, if you're stuck on a problem, here's what you can do. Draw a picture. There's a simpler problem out there. Try to find that simpler problem and solve that. But Polya's writing is about how problem solving works. The creativity behind problem solving. But at some point, Polya has to grapple with, how does learning happen from problem solving? So what if you've solved a problem? We solve problems all the time, and that doesn't always enable us to do something new. So his answer is, you got to reflect on the solutions. You have to think about the solutions that you come up with. If you solve a problem, you need to then really think about that solution that you've landed on. And that's a really sensible thing, I think. And it shows up in other research, contemporary research now. It kind of also sees that if you solve a problem, whether successfully or not, the learning that you're going to do that's going to enable you to solve more problems in the future more easily, and maybe with less creativity than you needed in this case, is going to come from thinking, reflecting on the solution. Well, I think that's super sensible. You need to think about the solution a little bit in order to learn from it. So let's think about this. This is a great kind of problem. I love it. I assign it. I took this one from solveme.edc.org. Yeah, I also love the mobiles. So the heart's way 2. The trapezoid is unknown. And we could give this to, I don't know what age kid to give it to, but let's assume that we're giving it to, I don't know, a child that doesn't know how to solve it yet, or any human who doesn't know how to solve it yet. But yeah, let's restrict ourselves to humans. Let's not go into animals or other creatures that might not, I don't know. But yeah, so a human person is trying to solve this, and they don't know. And I don't know how you would do it. It's worth taking a moment and thinking how you might go about doing this. There's more than one way to do it. And you might also wonder, if you have students, how would your students solve it? And I know, because I've given this to younger students, some of the younger students I teach, I sometimes give problems like these to them. And I do know a little bit about what I often see. What I often see is that what a kid would do is something like this. They would like add up 2, 4, 6. And once they understand, like, oh, each side needs to be balanced, perfectly balanced. So if the right side is 6, they would then say, oh, well, that's 2 over there, and therefore and what plus 2 is 6 is the thinking they would do. Look, that's good thinking. I got no problem with that. But I also teach algebra, and I know that that there's another way to solve this that maybe would be really useful for somebody who's learning how to solve equations. And it looks like this. It's that you could remove or ignore or group or match up the hearts. And okay, yeah, remove a heart from each side. Imagine removing a heart from each side, and then you'll be left with the trapezoid and the 2 hearts. That's fundamentally what we do when we solve an equation by subtracting something from each side, right? And so there might be a situation where a student would go about solving a problem like this, but I would really want them to learn this strategy. And so just going back here, so if the way that we learn from solving problems is reflecting on solutions, and if there's more than one way to solve a problem, then we sometimes run into an issue, which is that students would solve a problem, and it's great, and they use a wonderful strategy, and they land on a strategy that is just not the one that I want to teach today. Or they're not successful at all, and they remain stumped. Or they just don't think about the solution, that they don't reflect on it super well. So what do you do about this? The premise of a worked example is not that different from the premise of learning from problem solving. The premise of a worked example is, if you learn from studying a solution, then ask students to study a solution. And if you ask students to solve a problem, they will sometimes not be able to solve the problem and therefore not have a solution to study. Or they will land on a solution that's not the one that you think would be mathematically what you want to talk about today. And if that's the case, that is a lost opportunity for the student to learn something from studying the solution. So fundamentally, we got a picture that looks like this. The way that you learn from problem solving, according to Polya and other researchers, is that you reflect on the solutions. You think about the solutions. So what other researchers, what cognitive scientists that study worked examples posit, and what I think makes a lot of sense, is that when students learn from a worked example, it's the same thing as learning from solving a problem. But what's kind of cool about worked examples is that you're presenting the solution directly. So it's right there. The mathematical richness of the solution is available for consumption by the students immediately without having solved the problem. Now, I love creativity. I love problem solving. But there's a certain directness of this that puts students in contact with the problem, with the big mathematical ideas that I really do love and that I see exciting to students. Now, there's obviously things that you need to worry about. There's a lot of ways that this could fail, though. But let's start with this fundamental fact. Students, if they are going to learn from examples, if this is going to work, if they are going to learn from examples, then what's happening is they're learning from solutions to a problem, the same way you do with learning from problem solving. But you need to do more, right? You need to think about them, and you have to be able to generalize from them. The same kind of the deep reflection that Polya says you need to do. It's not enough to just solve the problem and see a solution. You need to think about it. We would need to do that same deep reflection with the solution from an example. So if we're going to learn from examples, it's got to be the same deep reflectiveness that Polya says you need to do when you're solving a problem and learning from solving a problem. You need to reflect. And I'm tempted to pause here because I know there's some questions, but I actually think that it's good to keep going because I gestured a little bit towards a moment ago to some of the ways that things can go wrong, that learning can not happen when you're solving a problem. You might not stop and reflect on the solution is one thing I mentioned. Another thing I mentioned is you might study a solution that's not new to you. You might land on a solution that's not new to you and never reflect on a new solution. That's what I was gesturing towards here, which is that this might be a great approach because it's great and creative and it's valuable and I love students thinking, but it might not be the one that helps you learn how to solve equations, which is what I think this strategy does. So problem solving has certain kind of, failure states, ways in which learning can not happen. Even though you're successful with problem solving, you might not learn anything from it. But there's definitely failure states. There's definitely ways that studying a worked example or studying a solution presented by a teacher, which is what I'm defining an example to be. There's lots of ways that studying a solution presented by a teacher can fail also, and it's worth it to mention like a bunch of them. Students might not understand the problem. They might not understand the solution either. The solution might be written in a mega confusing way that is distracting to students and doesn't make sense. Students may not be motivated to pay attention. They might not be into this. They might only study the solution superficially. They might look at the solution and just I got this. So there's not the deep reflection. There's not the trying to make generalizations that would help you apply this idea to other problems. And they might never make generalizations. Generalizations are, right, some of the reflection that you do when you successfully solve a problem. You have a specific solution in front of you, but how's that going to be useful to solving other problems? We got to do the mathematical thing of generalizing. Students might not do that when they're studying a solution. So, here we've done it. We've now answered both questions. We've answered both questions that I brought out in the beginning of this. I think we've got some simple solutions. Some simple answers to some relatively simple questions. The simple question was, why do students learn from studying an example? And the answer is, well, they do that when they think really hard about the solutions and they even make generalizations about that solution. Okay, great. Part one, done, check. Part two, why sometimes don't they? And the answer is a lot of things. There's a lot of things that can go wrong. To the extent that some educators say, forget it, don't do it. There's too many ways for it to go wrong. But that's actually not been my experience. And that's not what I think emerges from reading a lot of research about this stuff, which is part of what I did. Not really to write the book that I wrote, more just, the book came out of a lot of reading and a lot of experimenting in the classroom. And one of the things I saw is that right at the beginning of worked example research, which I think emerged from problem solving research in the 80s, in the 1980s. I mean, people have been studying math and learning forever, so to say, but the current strain of worked example research, I think, starts around the 80s. And like right away, people notice that sometimes kids don't learn from studying examples, or college students or whatever don't learn from studying examples. And the question's why? And Mickey Chi is like a really eminent cognitive scientist, and she was one of the first people to say, well, there's a lot of reasons. A lot of these things on this list were identified by her early on, and so what's cool is that if you look at some of the research, there's some answers. There's some kind of ideas, and I find them very practical about how to deal with some of these failure possibilities. So there's no perfect answers in education. But if we got this kind of relatively simple idea that kids learn when they think about solutions really deeply and they make generalizations from them, and we got all these ways that cannot happen, then we can like think of techniques that might allow kids to think really deeply about solutions, to help them be motivated, to write them in clear ways, to help them understand the problem, to help them make generalizations without falling into these failures. So that's what I want to spend the rest of our time together doing. I want to talk about what I've done in my teaching, inspired by research that I've read, to deal with these, these failures. So going back to the title of the talk, to try to figure out ways to preserve for my students the things about worked examples that are useful to learning, that it's a direct presentation of a solution that they can study really deeply and then generalize without all these, my hands are right now are like pointing at the screen, like all the things that can go wrong. All right, so that's what I want to do. Let me just, okay, there's a couple questions, and this might be a good, let me pause to read some of the questions. So how would I define learning was a question. And real briefly, the way I'm defining learning right now is kind of narrowly. Not defining learning. Learning, I don't know what learning is, but what I'm talking about is learning to solve problems, learning to solve new types of problems. And I'm not, and I mean that kind of in a big way, relatively big way. I mean, everything from like what we call skills, things that are so definite that you might call them algorithms, like really specific procedures, things that are a little bit bigger, like there's some choices you have to make. Like for me in my teaching life, I always think of solving systems of equations, simultaneous equations. There's some thinking you got to do. There's some creativity you might need, but ultimately it's fairly well defined, the kind of problem space, to things a little bit woollier where you might have some real choices to make. That's the kind of stuff I'm talking about, solving new types of problems. Like I'd include puzzles or whatever there. If students don't solve the problem themselves, how do they make sense of the solution? I can't wait to talk about this. This is what my talk's about. The second half is going to be some ideas that I have for that. Okay, respond to this statement. I believe that if problems can be solved with different strategies, the students should use the one that works for them. I don't have a response. I guess maybe depends on the situation. I have a lot of thoughts about that actually, but it depends on the skill for me. Like I teach third graders, and sometimes you see kids who are in third grade still like counting by ones to subtract, and that's great, but I want to help them learn more things. So I guess define works for them in that sentence. Anyway. So here's the two techniques that I find mega impactful, super duper helpful. There's more, and I definitely go into more detail in other places, definitely my book. But two things that that emerge from research and that I find really helpful. And the first technique is, if you're presenting a solution, don't just explain it. I mean, honestly, a lot of the time I'm not doing a lot of explaining in this. I'm asking students to study it, and then I'll prompt them to explain it for themselves, or to generalize things for themselves, or to ask them to critically think about generalizations. So if an issue, a way that worked examples can fail for students is that they don't think deeply about them, or they don't make sense of them, I will nudge students to to explain them or to generalize from them. And I want to get practical about that. The other technique is to find immediate ways after studying a solution for students to apply those ideas immediately. So we're combining some problem-solving practice, not necessarily problem solving in like the creative sense, maybe more narrow problem solving, but we're combining a chance. We're following up with an example with a chance to use those ideas and apply them, which also, if the problem looks a little teeny bit different from the problem and the solution, can also nudge students to make those generalizations and see, oh, the idea here is not just applicable here, it's also applicable here, where with my hands I just gestured to a space. It also often helps with motivation a little bit. There's a chance to use it right away and to feel like, hey, I'm getting good at something. And there's also kind of a nice kind of like, wait a second, do I know this? If I can't solve this problem, did I really understand this a second ago? Maybe I need to go back and study it some more. I see in the chat there's some discussion about the semantics of the word nudge. And that might be a different talk. That might be a different discussion. Anyway, so I want to get practical about this because I think about this stuff a lot. I teach, 5 classes a day, and each class is another chance to think about these techniques. So I've been thinking a lot about them. So I teach fractions to my youngest students. And I think this was last week or 2 weeks ago, I can't remember. But we're talking about equivalent fractions. And I wanted to help my students learn something that they didn't know how to do, which is use diagrams to find equivalent fractions. And what I did first is I showed this. I posed the question. I said, how many sixths? Well, I said is equal. I don't know if that's grammatically correct, but how many sixths are equal, is equal to 2/3? At this point, my students, my third graders, knew quite competently, I think, how to shade in 2/3 of a diagram. And they can, but I don't think they could have done this yet. They didn't know how many sixths were equal to 2/3. They don't have a procedure for this. I wanted to show them how they could use diagrams to figure this out. So I asked them, how many sixths are equal to 2/3? You might have an idea, I said. Put a thumb up if you understand the question. You might have an idea of how to solve this, but right now I'm going to show you someone else's solution. Here's how somebody else could solve it. I've seen this solution before, I said to them. I shaded in 2/3, and then I showed them, with not saying anything, that you could divide this into further sixths. And then really silently, I wrote down 4/6, the 2/3 equal to 4/6. And then, so that's the worked example. And immediately though, I prompted students, I nudged students. Maybe I'm trying to make nudge a technical term. I'm going to go for it. But immediately I follow this up with a question. I say, okay, I'd like you to explain this. This was an online third grade class, which is about as fun as you think it is. I asked, how do we know that 2/3 is the same as 4/6? So I prompted students to explain this. Now, this is an idea that shows up in the cognitive science research. Mickey Chia is, I think, the first to kind of identify this as a good strategy. Ask students to explain the things that they see in a worked example. The reasoning behind this is kind of interesting. Mickey Chia, these researchers were listening in on students. They asked students to talk as they were watching them read worked examples. And one thing that they noticed is that there was a difference between students who could later on go on to solve other new problems correctly. One difference that they saw was that students who later on went on to be successful using these ideas to solve new problems, that these students often paused while studying worked examples. They would say, why is that true? Oh, wait, yeah. Or they'd say, I don't think I understand. Oh, yeah. So there's this pausing and self-explanation that is very productive and very helpful for forming generalizations that successful students do more often than students who don't learn from examples. So just going back to Polya, some students spontaneously reflect on solutions, whether they know how to do this or whether it's because they know what an explanation sounds like or because they have a lot of prior knowledge, whatever. Successful students are doing this. And students who are successful applying these ideas later are doing this more often than students who aren't. And you've seen this. You've seen how sometimes students who are not going to go on to be successful solving a problem kind of are like, yep, I got this. No problem. I'm good. Yes, fine. I'm done. I got this. Whereas students who will go on to be very successful applying these ideas kind of will agonize sometimes and will think, wait, do I really get this? Do I? Well, I'm filling the gap. I'm asking the question that every student should ask to themselves, which is, why is this true? And my students at this point were able to more or less give explanations. I think there's actually a lot to that about teaching students what good explanations can look like. More on that soon. But then I asked another question. I said, again, there's kind of like little pushes to make generalizations. I said, okay, what if the question were a little bit different? Now in the chat, I said to my third graders, I want you to pretend that instead of asking about 2/3, I was asking about 1/3. And my question was, how would the answer change if instead of 2/3, it said 1/3 in the problem? How would that change? Again, I'm trying to push students to think about the global implications of the pictures that they're studying. So that's technique one. Technique one is prompts to explain or generalize. Technique two is immediate applications. So once I've asked students to kind of generate these generalizations or to move closer to making generalizations, I immediately gave them a new problem that had one thing different, that it was, or maybe I guess two things, but as few things as possible different, while being, because I want it to be recognizable to the students. I want them to know I want them to be successful here. I want them to be able to apply the ideas they just saw to some and just thought about. The generalization they just came up with. I want them to be able to apply that successfully here. I don't want them to be stumped. I want them to be able to successfully generalize it, but I do need it to be a little bit different otherwise. So that's a kind of a sweet spot problem that is the very nature of teaching. It needs to be not too much, not too little, but here it is. And I asked them to apply it. I said, how many eighths are equal to 2/4? And what they need to do here is they need to do the same splitting up idea that was done a moment ago, and they need to apply it here. This is different than how I used to do things before I encountered research, just by the way. And look, there's more than one way to get ideas. I'm not saying this is like specifically the only way to get this idea is from research. But as it happens in my life, what I tended to do was I tended to not follow up examples, explanations, studying solutions, whatever, the discussions. I didn't follow these up with chances to apply the ideas immediately. And that's a big difference in my teaching, and it makes a big difference for my students, I believe. I think it gives them wins. I think it gives them moments of feeling confident. But I think that confidence is really tied into their success in applying the problems to something new. And then this wasn't the end of my lesson. I had another activity, but this is the end of the cycle of things that I did relating to this work example. So it started, just to go back, I posed the problem and I made sure everybody understood it. So I'm trying to make sure that it's meaningful to students. I show the solution, trying to directly show this new mathematical idea. And then I prompt students to make meaning out of it, to give an explanation. I nudge them to make generalizations. And then I'm also nudging to apply it to a brand new problem. And I'm moving them closer to independent problem solving, which is the goal. All right, so this is third grade. I think what I have next is this same two-step pairing of these techniques with an example. With, I think, something from my calculus class. I think what I have here is, yeah. So this is my first time teaching calculus, so this might be rough. But these are students that really like getting a lot of practice, and we've been trying to get better at integrating. So this is an example that I recently gave my calculus students. And I asked them to study. I showed the problem, which was familiar to them at this point, which was to find this integral, which I don't know, which is equivalent to finding the shaded area, this green area. It's the area between 0 and 2 under this line, 10 minus 2x. And the new idea that I was trying to teach them is really conceptually difficult. And it's to use the kind of algebra of integration to find that area. Okay, so I said, here's a solution. I'm going to be quiet. I want you to study it. I want you to put a thumb up when you're ready to talk about it. And then I showed these prompts again, these nudges. What if the limits of integration, instead of being from 0 to 2, were 0 to 5? How would that change things? And I asked another question. Where will the area function be at a maximum? That's this function over here, the area function, 10x minus x squared. Where will that be at its greatest value here, and how come? And those are my little prompts, my nudges for thinking. I asked them to turn to their partner. In this case, this was an in-person class. So I said, I assigned partners, and I said, I want you to talk to your partners and discuss this. I want you to talk about this until you all agree. Actually, let me pause for a second and give you a second to read this, because there is actually quite a bit on the screen. Actually, would you like a chance to try to answer these questions? Might be fun. Totally optional. I don't really know how. I have no sense for how well all of us remember calculus, which is, before I taught this class, not very well. And so I'm going to pause for like 10 seconds. What I'm doing here is, again, trying to encourage kids to fill the gaps a little bit and to think really deeply about this. Now, what I really wanted to share here was, but this was a time when, so that's the first technique. And whether the content here makes like 100% sense to you or not, depends on your calculus background, honestly, and your calculus current knowledge. My calculus background was okay, and my current knowledge was like low, and now it's like a little bit better. But this is like not that different from what I did with the third graders, with the prompts. What I did next was a little bit different. Because technique number 2 is immediate applications, but this is super complicated as far as the procedure goes for my students. This was not easy for them. This was really hard. These are students who opted into a lower stress calculus class, often because they're not like 100% confident in their algebra. So this was kind of complicated, and they needed time. Somebody in the chat asked for some more time to read this. My students definitely wanted a lot of time to read this, and to ask them to just solve a similar problem right away, as I did with the third graders, would have been a disaster. So I needed something else. So there's another like modification of this technique that I really like, which is to, so what I showed them was, I said, okay, now I'm going to show you another almost complete worked example, another problem that I've almost written the whole solution to, except I haven't done the last step. And I left it out, and I said, go ahead, read this until you're super happy with it, and then try to finish the problem. And then I did this again with another problem. And then again, and each time I would remove a little bit more. And what I love about that is it gave my students a chance. So this is another idea, like cribbed from research, from cognitive science research, from worked example research. And it's called kind of like, it's similar to concreteness fading. I think is the more common thing you might call that. Well, no, concreteness fading in math education means like you got like a physical object and you abstract it. This is fading parts of a worked example so that there's more and more that students can do on their own while still giving them a chance to focus on just one bit of it, so that a skill that involves, for example, making sense of function notation, not a given for my students all the time. It gives them a chance to work on that portion of this in the context of this nice, meaningful application problem. And by application, I don't mean like real world application. I mean application of the idea from the previous solution. So what I'm saying here is that if students aren't ready to do an immediate application, I still, of like immediate solve the whole new problem, I can still give them an immediate application by giving them kind of a little snippet of a problem to complete on their own. And this is part of that second technique. Oh, there's a question that I want to address. Am I intentional about how straightforward these questions are? There's a little context. Is this done to reduce extraneous load? And this was a question earlier, but it could apply now. And no, these are, I'm just trying to pick examples from what I happen to be teaching in the last couple of weeks. This is not only about like, I guess, super straightforward questions. I also wouldn't call these super straightforward for my students. Like the fractions one is not at all straightforward for my students, for my third graders. This is kind of a really meaty question that they could think a lot about, and that they do think a lot about. But this is for when I want to teach them how to do this. I don't know if I addressed the question, but that's my attempt. I want to show you one last kind of thing for my classroom before wrapping up. And so I also teach high school geometry. And this is from the beginning of the year. And this is a different kind of prompt. So this is my attempt to use that first technique in a slightly different way. This is a circle. O is the center. I'd tell that to my students. And there's a lot of angles. And one thing I want to teach in geometry is I want my students to be able to find missing angles. And I want them to know about inscribed angles. Inscribed angles are these corner angles. You may or may not remember from geometry that there's a really cool relationship between these angles and what are called central angles, like the clock angles in the middle. So if this is 80 degrees, this is 40 degrees. And this is a question that I asked my students when we were studying this. I said, what would be the best explanation for why angle B is 40 degrees? And I gave them two options. I said, option A, isosceles triangles contain two equal angles. Is that a good explanation for why angle B is 40 degrees? And my second option is inscribed angles are half the degrees of their arc. So what's going on here? I want students to be able to make generalizations. I want students to be able to look at a solution and reflect deeply on it. And part of what that means is if they're going to be able to apply it to other problems, they need to be able to say, oh, it's not just this solution. This isn't just going to be true here. It's true for a lot of other things too. A lot of other cases. There's an idea here that this represents that's generally true. It's not just specifically true here that this is 40 degrees. It's generally true that, and there's something larger. Okay, a challenge, kind of like the challenge with a complex procedure that my students don't know how to do on their own yet, even after studying a solution, is that students don't always know what a good explanation looks like. And I get this. So the more often you ask students to explain things, the more often you'll hear kids say, I don't know how to explain it, but it's true. That's, I think, a sign that we need to teach kids what good explanations look like. So here's a kind of prompt that's a nudge. It's a nudge towards deeply reflecting on a solution. It's a nudge towards generalizing. And it's by studying a solution, not by problem solving. So I asked students, and this was an online class, but I've also done this in person, what's the best explanation for why this is 40 degrees? And these are two generally true principles, right? It's true that isosceles triangles contain two equal angles. That's a generally true principle. It's also true that inscribed angles are half the degrees of their arc. That's also true. That's true for all circles. That's a theorem that that my students have studied, they thought really hard about this. There was some interesting debate. Some students really liked the idea that isosceles triangles can do equal angles, that A explains this well, and I totally see their point. After all, there's really an argument that B and A are super related. But B is a really good explanation too, and it really related to what we have just been discussing in our class. Now, what I like about this structure is that these are two generally true principles. I'm asking students to connect this solution to a generally true principle. I'm modeling for them in a rather direct way what a good explanation could look like for why this is true. I'm just merely asking them to think about which one applies here. So I feel that what I'm doing here is I'm scaffolding that generalization the same way that I kind of scaffolded the try this on your own aspect of this problem. This is, I think I took this from research also. I definitely took the spirit of it from something I read in Bethany Riddle Johnson's papers about scaffolding explanation making. I think I even took this structure and ran with it a little bit, but I love this. So at this point, oh, I did this again. Oh, good. This is an algebra example. Another time that I did this towards the beginning of this academic year. Which reason explains why you can write a divided by b as a fraction, a over b, something that I find my algebra students really have a hard time with and that I need to help them with. So again, two generally true principles. And I'm asking which one applies here better. I don't know if there's, maybe, I hope here that maybe I should pause. Is there a clear answer here? All right. When you divide by b, it's like making your starting amount b times smaller. And the second option is you can remove the same amount from both sides of an equation. Those are both generally true. Which of those generally true principles animates this one, gives this one life, explains why this one's true? I think it's A. I think A is nice here. I think A is a general principle that you could connect this one to. And I think B is clearly incorrect in this case. That would not be a good explanation for why this is true. So I think in this case, I'd want everybody to try to answer A if they want, you know, a successful answer. I think A is the better explanation. And I like this because I'm teaching explanation. I'm also giving them a chance to generalize, to say, no, the thing that's always true here is that when you divide by B, you're making your starting amount B times smaller. And so that's why you can write 11 divided by 3 is 11 over 3. So where I'm at is I've got some go-to prompts. I've got some, I've got these two techniques. I've got worked examples, which they work when you think really deeply about them and make generalizations, but there's a lot of things standing in the way of them successfully doing that, successfully thinking really deeply about it. And so one thing I do, following the advice of some researchers, is that I prompt students to self-explain and to generalize. And here's some of my go-to structures, as you saw from the stuff I just kind of pulled. One of the questions I ask is, how would the answer change if I changed this? The kind of what if question. What if instead of this, it was this? Another thing that I often do is, which reason best explains why this works? That multiple choice, which reason do you like better? Another structure that I kind of glossed over earlier, but that I also think is kind of powerful, is I'll point out a connection they might not have noticed, and then I'll say, explain it. Did you notice that there's, oh shoot, I shouldn't, well, I was kind of thinking that this is one thing that I do is like, I think that came up over here. But no, I was thinking of a different thing that I did with my calculus class, where I asked them to imagine what they were doing on a graph. So I said, you know, what would this look like? What shape would this look like? Explain why it would be a triangle or whatever. I'm imagining something in my head that I'm not communicating super well, so I'm just going to pause on that. But the structure is true. Notice this connection. Notice this thing that you didn't see right away. Explain why that's the case. Because I'm pointing out something they might not have noticed, and then I'm also asking them to give it some life, to generalize from it. And then when it comes to this other technique of quickly applying the idea, I'll do one thing I'll do is that I'll assign a new problem that very subtly changed, like I did with the fraction thing, like just enough that you need to think about how what you just saw would apply here, just enough. And when that's not possible, because it's too much, it's too complex, it's too much to bite off all at once, I'll scaffold that. And the way that I'll do that is I'll still give them a chance to solve the problem on their own, just a little bit of it, and in the context of another example, so that it's still a meaningful solution, but you're filling in a little bit, and you're able to focus on building up to complete independent confidence. We're near the end here. I want to just give credit to Algebra by Example, the same people behind Math by Example. Julie Booth is, I think, the lead researcher there. And their resources are free. And they also have this structure also, because this is a nice way to learn from studying a solution. These are materials. It's not a pedagogy, exactly, right? There's advice, but what you can see is there's a solution focusing on something that the kids could really benefit from learning. A lot of algebra students need help explicitly learning how to combine like terms, or even, I don't know if that's like terms. I don't know if it's whatever. +2 - 5 is something that combining addition and subtraction is something kids benefit from seeing explicitly. They ask them to explain it, and they ask them to try it on their own. This is the 3-part structure that's kind of at the heart of how I'm using learning from solutions. And so if we want to discuss things, there's a couple questions. The question I'd leave you with for you to think about is, so here's a worked example, another one that I pulled from my geometry class. Could these 3 lengths make the triangle? And I tried to draw a picture that would represent a way of thinking about this. One that I've seen kids use. And you might think about, I want to take a look at the questions that have shown up in the chat, but you might think about, how would you prompt students to think more deeply about this? How would you ask them to reflect on it? How would you ask them to explain it for themselves? And how would you help them make generalizations? What's a prompt you could use to help them think about making a generalization from this? My experience in my own class is that kids love this stuff. They love feeling empowered that they understand something new. They love the chance to make sense of it. They love the chance to analyze it, and they love the chance to use it afterwards and feel like there's something brand new that I just learned and that I'm able to apply it just to something challenging. So all these things, the explanations, the analysis, the generalizations, the applications, it's been great for my teaching. I've written a lot about this, and I'm excited to talk more about it. I'm excited to see if people have any thoughts about this. There's a question in the chat, so we're now, I think, in question time for the next couple minutes. Is that?
Yep, that sounds good.
Sounds good. Okay. Can I offer any advice for the don't understand the solution, and the solution is written in a confusing way dilemmas? Yes. Okay, first of all, you should buy thousands of copies of my book. It's important to just like millions of copies. Just do it. I don't know. I'm joking about all that, by the way, just to be 100% clear. Anyway, so I do describe this a little bit in other places. And here's what I'll say. I'll say that you need a strong routine, and not understanding the solution and writing confusing solutions. There's an art to writing clear solutions. Part of that art is being modest and being specific about what you want students to learn. There's a lot of, if you're interested, there's a lot of great summary documents that you're gonna have to tweet me for, because I can't think of them off the top of my head, that summarize some of the design principles that researchers have landed on, like media researchers, people who study clear ways of presenting ideas in video or writing or in examples, have landed on for like clearly designing these things. But I think the most important one is just focus on, if something's confusing, there's probably a smaller, it's like the polio problem, right? If you've got a complex solution you're trying to teach, there's probably a smaller mathematical idea there that you want to focus on first. and it could probably make a briefer solution. And a briefer solution could probably be clearer for students. In terms of helping students understand, I think these techniques that we were talking about tonight do help kids make meaning and understand the solution, even if they don't at first, but there's more to it. Students might not understand a complex diagram, and then you have to get into more complicated things. Like what I often do is I'll often, before showing a solution, give kids a very relevant problem to solve on their own that maybe it's a review problem. Maybe before showing a solution that involves calculating a slope, I'll ask them to find a bunch of equivalent fractions as a warm-up, because that's going to be super important for making sense of the solution that they're studying. So there's a lot to thoughtfully designing a lesson that will lead students into a solution that makes sense. I think these two techniques are two of the most impactful ways you can do that, but I definitely found warm-up problems to be super helpful. Let's see. Should I be looking at the chat? Or
I don't have any questions for you in the presenter tab, so
that's great. I can hang around. We can end things and then we can keep talking.
Yeah, I was gonna say, I don't think I see too many other questions in the chat. You did answer most of them earlier on.
So last chance is what you're saying.
Yeah.
Last call. Going
last
one.
Chance questions. Well, while we're waiting for those people to come up with those last minute questions, let me just mention that our next session is on May 4th, and it's going to be presented by Robin May. It's a session that is recommended for grade pre-K through 2, and the title of the talk is Games and Routines for Building Number Sense and Fluency. I don't see any questions from anyone.
That's great.
So
be in touch. If
you have any questions, definitely reach out to Michael through email. I'm just going to wrap things up. So if you have another question or two here, you can feel free to type it in the chat. But I'm very grateful for Michael for his sharing with us tonight. And for everyone in attendance, thank you for joining us tonight as well. One other additional announcement is that we are looking for Global Math Department webinar attendees to share how the Global Math Department has impacted their work in their classrooms. The webinar will have approximately 4 presenters sharing for about 10 to 15 minutes each. And we are interested in hearing from people that attend the webinar live, watch the recording, or listen to the podcast. Consider sharing with us for this special session on June 29th. If you're interested, you can email us at globalmathdepartment@gmail.com, or you can fill out this Google form, which I'm going to paste the link into the chat. Right there's our Google form. And I do know we have 2 people already that have expressed interest, but we're definitely looking for other people as well. So thank you very much. And thank you, Michael.
Thank you.